a couple of problems in today's class, and then we will go to the next topic also. So the topics that are left over still in this particular module are flow over bank of tubes. Currently, what we are seeing is flow over surfaces. What we have seen is a flow over flat surface. Then we will see flow over curved surfaces, and then we will also have flow over bank of tubes. Bank of tubes is basically a collection of tubes where the concept of the flow over surfaces will be applied, but in a larger scale, in a collective scale. And then we will go to flow through pipes, internal flow situations. So that will be the end of module, this particular module 4. Then we'll go to the next module, module number 5. So we share the presentation so that we can start solving the problems here. So we'll take up this particular problem for today's class to begin with. So here we have nitrogen gas at 0 degrees Celsius is flowing over a 1.2 meter long, 2 meter wide plate maintained at 80 degrees Celsius with a velocity of 2.5 meters per second. For nitrogen, the properties are given. Find the average heat transfer coefficient and the total heat transferred from the plate. So this is one of the simplest types of problems that are possible to solve in this forced convection, especially over flat plates. So we have a plate, a flat plate maintained at a constant temperature of 80 degrees Celsius, and there is a fluid, which is nitrogen, flowing. So the plate is hot, fluid is cold, and we are asked to find out the rate of heat transfer and also the average heat transfer coefficient. So if you are able to find the average heat transfer coefficient, then finding the rate of heat transfer will be easy. Okay, so first thing to be done is to find out the heat transfer coefficient. So in any problem of this nature, especially flat surfaces, the first thing you check is whether the flow is laminar or turbulent. So, but even before getting that, the best way is to start with a schematic diagram. So we have a surface temperature of 80 degrees Celsius. There is this nitrogen flowing at a temperature of 80 degrees Celsius. And what's the velocity? Velocity 2 meters per second. And the length of this plate is given 1.2 meter long.
So nitrogen is 0 degrees.
Sorry, nitrogen is 0 degrees. Plate is 80 degrees Celsius. So we have TS, or you can call TW also, as it is called in the data book. TS is 80 degrees Celsius. T infinity is 0 degrees Celsius, and some properties are given. So density, Cp, and viscosity are given, and thermal conductivity also are given. So first thing is you need to calculate the Reynolds number. Reynolds number is rho V. In this, the characteristic length is L, rho V L by mu, or VL by nu. This V is velocity, this nu is kinematic viscosity. So in this problem, we are given the kinematic viscosity. Okay, so we can use that and find out. So velocity is 2 meters per second, length is 1.2 meters, and the kinematic viscosity is 15.63 multiplied by 10 power minus 6. So calculate this value. The velocity is 2.5 meters per second. 0.5. What is given in the problem? So how much is that? This is 1.919 multiplied by 10 power 6. Now this is the Reynolds number, and we need to decide whether this is a laminar flow or turbulent flow. So we have to compare with the critical Reynolds number. Critical Reynolds number is 5 multiplied by 10 power 5. So our this is 10 power 5. So this is 1.9 or 2 multiplied by 10 power 5 approximately, and this is 5 multiplied by 10 power 5. So this is less than the critical Reynolds number. Therefore, the flow is laminar. Therefore, we have to use the correlations that are meant for laminar heat transfer. Okay. So the equations that are available for laminar flow over flat surfaces are like this for a constant wall temperature. So for constant wall temperature, the correlation is available in page 121. So it's given as a Nusselt, the local Nusselt number is equal to 0.332 multiplied by Reynolds power 0.5 and Prandtl power 0.333. Okay, so this gives the local Nusselt number. The average Nusselt number is what we want, is equal to 2 times the local Nusselt number. So this you need to remember because I didn't find it in the data book. So it's important to remember that. So once you have the local Nusselt number, you can calculate the average Nusselt number. But for the local Nusselt number, you need the Reynolds number, which you already have. But the Prandtl number is not there, so we'll have to calculate the Prandtl number. So Prandtl number is Cp mu by K. Okay. So we don't have mu, but we have nu. Relation between dynamic viscosity and kinematic viscosity, you need to find out. So dynamic viscosity is kinematic viscosity multiplied by the density. So this is Cp multiplied by a rho nu divided by K. So Cp is 1.04 kilojoule per kg Kelvin. So 1.04 multiplied by 1000. Density is 1.142 multiplied by kinematic viscosity is 15.63 multiplied by 10 power minus 6. This divided by the conductivity is 0.0262. So this will give us the Prandtl number. So .708. You see, some interesting thing that you can notice is if you turn to page number 44. We can start from page number 42 in data book. Page number 42, open that, and you see there are property values for different gases at 1 atmosphere. Okay. Now you can see we follow the Prandtl number value for all these gases. Whatever may be the gas, you see for air, it begins with 0.728 and goes to 0.724. So it's around 0.7. Similarly for nitrogen also around 0.7. 0.665 is the least, but it's going up to 0.79. So what is happening is for most gases, the Prandtl number, especially at ambient conditions, the Prandtl number is very much close to 0.7. So like we calculated here. Okay, so if you don't have access to data book and if you need Prandtl number, you can safely assume it to be 0.7 and you will get a reasonably good answer. Okay, so that's something you need to remember. All right, now we'll get back to the Nusselt number. So local Nusselt number is 0.332 multiplied by Reynolds number is 1.919 multiplied by 10 power 5. This raised to power 0.5 multiplied by Prandtl number, here it is 0.708 multiplied by 0.333. See, 0.333 is nothing but 1 by 3. So you evaluate this. Is 129.6 is the local Nusselt number. So the average Nusselt number will be 2 times the local Nusselt number. So this is 2 multiplied by 129.64. This is 259.3. Okay. So the average Nusselt number is equal to the average heat transfer coefficient multiplied by the distance divided by K, or H is equal to the average Nusselt number multiplied by K divided by L. So this is 259.3 multiplied by K is 0.062 divided by L is 1.2. So this will be 5.6 watt per meter square Kelvin. Okay, so this is the heat transfer coefficient, the average heat transfer coefficient. Okay, now we will have to find out what is the heat transfer. Okay, so create a new blank slide here. Q is equal to heat transfer rate is equal to HEA delta T. Okay. Now, depending on whether the fluid is flowing on both sides of the plate or one side of the plate, the thing can change. Okay. So if this is a plate where fluid is flowing on both sides, then area will be area on one side is length is 1.2 meter long, 2 meter wide. So 1.2 multiplied by 2. On one side, the area is 2.4. Okay. So if it is on both sides, we'll have to multiply this area with 2 again. So 2.4 multiplied by 2 is 4.8. But anyway, if it is not mentioned that it's flowing on both sides, then we can safely assume that it's flowing only on one side. Okay, so in this case, we can take it as H is equal to 5.66 multiplied by 2.4 multiplied by delta T is 80 minus 0. So 1086.72 watts is the rate of heat transfer. Okay. Now, until this point, while studying conduction, you were given the value of the heat transfer coefficient right away. But heat transfer coefficient is not something that is directly available from the data books. You will have to work. You'll have to work to get it. So you see, we have solved some equations and put some effort in estimating the value of the heat transfer coefficient. So this much work is needed. to get that value. So this is all about the convective heat transfer. Finding out the heat transfer coefficient is the major job. Ultimately, if you know the heat transfer coefficient, calculating area, calculating the temperature difference is all easy. It's quite well known to us. Okay, so that's about this particular problem. Now we'll move on to the next problem. I'll just give a hint for this problem and leave it to you. So consider a rectangular fin that is used to cool a motorcycle engine. The fin is 0.15 meter long and a temperature of 250 degrees Celsius, while the motorcycle is moving at 80 kilometers per hour in air at 27 degrees Celsius. So the air is in the parallel flow over both surfaces of the fin, and turbulent flow conditions may be assumed to exist throughout. What is the rate of heat removal per unit width of the fin? So this problem also is a problem of a flat plate. Remember, fins are not necessarily flat. I mean, if you take the cross section of the fin, it's a kind of a conical shape with a flattened tip. So here we are supposed to assume it to be a flat surface or a flat plate over which fluid is moving. So in this case, fluid is actually not moving, it's the motorcycle which is moving. But then the end result is as if the fluid is moving over a stationary flat surface. So the both ways the effect is the same. Heat will get transferred by convection. Okay, so here we have a flat surface. Now in this case, fluid is flowing on both sides of the surface. Unlike the previous case, here we have both sides. So we have a T infinity of 27 degrees Celsius. U infinity is 80 kilometers per hour, and temperature is Ts is 250 degrees Celsius. And we are also right away told that the conditions are turbulent. We assume. So what is the rate of heat removal for the fin? Okay. So in this case, you don't really have to calculate the Reynolds number for the sake of determining whether the flow is laminar or turbulent, because you are already told that the flow is turbulent. But ultimately, you will have to use the correlations meant for turbulent flow heat transfer, and in that you will have the Reynolds number. So you will have to determine the Reynolds number, but not to find out whether the flow is turbulent or not. So for turbulent flow conditions, you'll see in page 122 of your data book, equation set 1.4.1. Fully turbulent from the leading edge. So there you will see the Nusselt number, average Nusselt number is 0.037, Reynolds number 0.8, and Prandtl number 0.33. You will have to use this equation. So Reynolds number, you will have to find out. Now, in this problem, we are not given the value of the properties. So we'll have to look up for the properties. The fluid is air, so we'll have to look up at air properties. But at what temperature should you see? Now, you will see that at the top of this particular chapter in data book, page 121, you are told that the properties must be evaluated at film temperature, TF. So properties at the film temperature, which is the average of the surface and the free stream temperature. So Ts is 250 plus 27. So 277 by 2. So this is approximately 140 degrees Celsius. So you'll have to read the values, property values at 140 degrees Celsius for air and use them in this calculation. So you'll have to calculate the Reynolds number, rho V L by mu. Prandtl number you can look up again in the table and you will find it close to 0.7. Can be safely can assume that. So once you do that, you will get the Nusselt number. Once you get the Nusselt number, Nusselt number is average heat transfer coefficient multiplied by L divided by K. So from this, find out the value of H is equal to Nusselt multiplied by K divided by L. And once you have the Nusselt number, you can find out the value of Q. Q is HA delta T. Okay. But in this problem, as I said, we have to consider both sides because air flows on both sides of a fin. And area is it given? Are we given? The fin is 0.15 meter long. So it's a small fin, 15 centimeters long fin. And we are told to assume the width as the unit width of the fin. So 0.15, right? Okay. So you have to calculate this H multiplied by 0.15 multiplied by the unit width of the fin. This is area on one side. Multiplied this with 2. This will be the area on both sides. Multiplied by delta T is 250 minus 27. And whatever H you get, you'll have to use that. So whatever answer will be watt per meter width of the fin. Okay, I leave the rest to you to work it out.
Sure.
Now,
Why is the Nusselt number changing from the previous question to this?
Nusselt number changing or Nusselt relation changing?
Yeah, relation.
Nusselt relation, because the earlier one we had laminar flow. This one is laminar flow, and this one is turbulent flow.
Okay.
Yeah. Now we'll come to flow over non-flat surfaces, flow over cylinders, flow over spheres, and so on. So this also is important because flow over cylinders, you will see flow over cylindrical surfaces when you deal with heat exchangers. In heat exchangers, especially the shell and the tube heat exchangers, on the shell side, fluid flows over the tubes. So that's one application. In spheres, flow over spheres, you see, just imagine lead shots or steel ball bearing balls, steel balls that you see, when they are made, they're at a hot condition and they have to be quenched. And to quench them, they have to be subjected to some cooling medium, some flow of air or some flow of liquid and so on. So there, the condition is flow over spheres. So we have these situations where the flow takes place over surfaces which are not flat. So what happens here is in these surfaces which are not flat, which are curved like this, you will see the flow pattern in this manner. So this is, imagine this is the surface and this is the free stream flow taking place. So as the flow approaches the object, which is a kind of a bluff body, so it doesn't allow flow past it. Therefore, flow has to take a deviation. So flow will take a deviation, and in this way, what happens is after a certain point, the flow gets separated. The flow gets separated from the object. So you see here, before on the front side of this, on the upstream side of the object, you can see the flow layers are quite aligned with the surface of the object, but on the wake side, on the back side, which is called as the wake, the flow is not so aligned, and you see the small curved arrows. These are called as the eddies. So this eddy formation takes place because of the flow separation, because now the flow is separating away from the curved surface so that it can catch up with the rest of the flow. Now this eddy formation is not not desirable because this is area of loss, a low energy region. Therefore, whenever in many cases, whenever we design objects over which fluid is supposed to flow, we make this as a streamline. We extend this so that the flow separation is not taking place. Flow separation is delayed as much as possible. So that is why we have this streamline flow, aerofoil shapes, and so on. Okay, so on a cylindrical surface or on a spherical surface, you will see that this flow regime is divided into one region, which is called as the favorable pressure gradient region, and the backside region is called as the adverse pressure gradient region. So in the favorable pressure gradient region, we have this pressure gradient, which is less than 0. Remember, flow takes place in the direction of decreasing pressure. So flow takes place from higher pressure to lower pressure. So that is called as the favorable pressure gradient. Here we see dou P by dou X is less than 0. That means pressure is decreasing with increase in X, with increasing in distance. So therefore, this is a favorable pressure gradient. And in the regions of the favorable pressure gradient, the flow remains attached to the surface. But as the flow goes to the other side, the pressure gradient becomes adverse and the pressure gradient actually increases with the increase in distance. So you see this this velocity profiles you see here, the velocity profile is quite well attached and it is in the direction of X. But as the flow separation takes place, as the pressure gradients become adverse pressure gradient, like you see here, then you see the velocity profile, part of the velocity on the top is in the direction of the flow, but the remaining is against the flow direction. So, but ultimately the majority of the flow has to go in the direction of the flow from left to right in the direction of X. So what happens is there is some kind of a vortice is formed because you see some part of the flow is going in the X direction and some in the reverse direction. Flow reversal is taking place. So the point at which the flow separation takes place, there you have this condition, boundary condition as du divided by dy is equal to 0. That means the gradient at this point, at the point of contact, the velocity gradient is equal to 0. That is where that's the point where the flow separation initiates. And as you go forward, the flow separation and then the flow reversal takes place, a deformation takes place. Now, because of all this, what happens is there will be certain drag force, and the drag force keeps varying at different distances, at different points on the object. For example, you see we have a tennis ball. So on the tennis ball, if the tennis player had to serve it at a very high speed, or similarly we have cricket ball. If we have to bowl at a very high speed, because that is desirable in some cases, then the amount of resistance to the flow, that resistance is called as the drag force. That resistance to the flow should be as low as possible. So to make the flow the resistance as low as possible, the drag should be as low as possible. That means the flow separation should be avoided, or if not possible to avoid, we should delay it as much as possible. That will reduce the drag force. So you can see here let us say this can be a spherical object or a cylindrical object. The behavior is similar. So here we have external flow over a cylinder. You see there is a flow taking place with the Reynolds number less than 2 multiplied by 10 power 5. So at this point, that means this is a kind of a laminar flow. So what is happening? The flow is approaching the object, and at this angle, the flow separation starts taking place. That means this entire region is a region of eddies, and this contributes to a large amount of drag force, which is quantified by the coefficient of drag or the drag coefficient. Okay, so if the velocity is high, then the Reynolds number also is high. So now in this case, the Reynolds number is greater than 2 multiplied by 10 power 5. In this case, you see the flow separation has gone behind the object. That means the flow separation has delayed. And if you go for a much higher Reynolds number, you may actually avoid the flow separation. So if you are avoiding the flow separation, then what happens is the drag force will be very, very low. So you see here in this figure, the Reynolds number is given on the x-axis and the coefficient of drag is given on the y-axis. So you can see two curves. One curve is for a spherical object, another curve is for a cylindrical object. So you can see here as the Reynolds number is increasing, the drag coefficient is decreasing. So initially there is a very rapid drop in the drag force, and after that the drag force drop is not so drastic. It's kind of becoming flat. And for a very, very high Reynolds number, there is again a drop, and again there is a small rise in this region. Leave this 10 power 6 is very, very large Reynolds number. So we'll stick to this region up to this point. So you can see that for very high Reynolds numbers, the drag coefficient is very, very low, and the drag coefficient will determine what is the amount of drag force according to this equation. So if the drag coefficient is high, the drag force also will be high, and that contributes to the resistance that the object phases for flow. So if you are able to give a very high velocity to any object like a cricket ball or a tennis ball or a what is it, golf ball, then what happens is the resistance decreases. Okay. You also know that the golf ball has got dimples on its surface. That is, those dimples are deliberately kept so that these dimples will disturb the laminar region. So if the laminar region is disturbed, the flow becomes turbulent, and when the flow is turbulent, the flow separation is delayed, and therefore you will get a larger range of move of the golf ball. So that's the reason for that. Now, what are the correlations that we have for determining the heat transfer coefficient over cylindrical and spherical surfaces? So the general nature of the correlations are like this. Nusselt number, the definition is hd by k. D is the diameter of a cylinder or a sphere. hd by k is equal to some constant multiplied by Reynolds number based on the diameter raised to the power m, and Prandtl number raised to the power 1/3. 1/3 is 0.333. So this is meant for a Prandtl number greater than 0.7. Okay, and values of C and M can be found in tables. So if you turn to page number 124. So you see here 124, you'll actually see a table. Okay, so in this table, you are given a Reynolds number, range, and for each range of Reynolds number, you will be able to read from the table, you will be able to read the value of C and the value of M. So then you can use this particular equation. Also, a single comprehensive equation is proposed by Churchill and Bernstein for all values of the Reynolds-Prandtl, which is greater than 0.2. So another equation also is available, is possible here. So 0.3 plus 0.62 Reynolds half, Prandtl 1/3 divided by this value. And again, so this looks a little bit complicated, but it covers a huge range of these values. So many flow conditions can be simulated using this equation. For the equations above, the properties must be evaluated at the film temperature. So just like the flat plate, the properties must be found at the film temperature, surface temperature, and the fluid temperature divided by 2. In case of the sphere, what should we do in case of a spherical object? So for spherical objects, the coefficient of drag is 24 divided by Reynolds number for Reynolds number less than 0.5. So you see here in this graph, for Reynolds number less than 0.5, you see for spheres, it is 24 divided by Reynolds number. So this dashed line you see, that is what is given. Okay. But but somewhere in this region, Reynolds number less than 0.5 means somewhere in this region. This is 10 power minus 1 is 0.1. This 10 power 0 is 1. So somewhere here in between 0.1, 0.2, sorry, 0.1, 0.3, 0.5. This one at this value or anything less than that, we have the Reynolds number clearly defined as a 24 divided by drag coefficient divided as a 24 divided by the Reynolds number. Okay, then the Nusselt number is given like this: 2 plus 0.4 Reynolds half plus 0.6 Reynolds 2/3 multiplied by Prandtl power 0.4 multiplied by mu by mu s power 1/4. Now you see this particular ratio, the ratio of the viscosities will be used whenever the property variations are large. So what is mu? Mu is the dynamic viscosity of the fluid at the film temperature, and this mu s is the viscosity of the fluid, but at the surface temperature. So except mu s must be evaluated at the surface temperature, whereas all other properties must be evaluated at T infinity. So this particular equation is to be evaluated at T infinity, not film temperature, but T infinity. Okay, that's something you need to remember. Now, where do we find this equation? Flow over spheres. This is in page number 128. Equation set 3.2. You'll see this. For large property variations, gases and liquids, you can use this particular equation. And for freely falling liquid droplets, see, this is external flow of a sphere. I gave the example of steel balls in the ball bearing. So when they are being quenched, they experience certain heat transfer, which can be quantified using this equation. So you can predict the rate of heat transfer using this equation. For freely falling liquid droplets, for example, rain droplets, when they are falling, then you can use this equation to find out the heat transfer coefficient. So even though the rain droplets are not exactly spherical, for practical applications, we can assume that to be spherical. Okay, so these are some correlations that are available for heat transfer over flat surfaces and curved surfaces. Now, one thing I want you to observe is in the case of flow over cylinders and spheres, we never mentioned about whether the flow is laminar or turbulent. Okay, so the correlations that are given to you are irrespective of whether the flow is laminar or turbulent. You will have to apply different conditions to use the different correlations that are available. As far as cylinders are concerned, we will apply the correlations page on located in page 124. And for spheres, we'll use the correlations that are available in page 128. Okay, so now we'll work out this particular example. A circular pipe of 37.5 millimeter outside diameter is placed in an airstream at 30 degrees Celsius and 1 atmosphere pressure. The air moves in cross flow over the pipe at 10 meters per second, while the outer surface of the pipe is maintained at 95. So pipe has got a constant temperature and the fluid is at a temperature of 30 degrees Celsius. What is the drag force on the pipe per unit length? What is the rate of heat transfer from the pipe per unit length? So this again is quite a standard problem. So we have a circular pipe of diameter 37.5 millimeters. And over this, we have fluid flowing at 30 degrees Celsius and what velocity? 10 meters per second. And this surface is at a temperature of 90 degrees, 95 degrees Celsius. Okay. Yeah, that's the data given to us. So we'll have to find or we'll have to evaluate this problem. So what we will do is we'll follow the standard procedure. Remember, this is a cylinder, it's not sphere. So it's important to find out and apply the correlations for a cylinder, not that of a sphere. So the first thing that we need to do is find out the film temperature. Remember, the properties have to be evaluated. So the film temperature is 30 plus 95 by 2. So this is 125 by 2 or 62.5 degrees Celsius. So at the film temperature, I want you to look up for density, dynamic viscosity, conductivity, and also the Prandtl number. So quickly tell me these values. You may not find 62.5, or you may have to use an approximate value. Read the data book and tell me these values. What page to refer? This is air. So we have air properties and page number 42. The data book. So in page number 42, we have 60 degrees and 70 degrees Celsius properties. What we need is 62.5. So I'll use the values at 60 degrees Celsius only. So density is 1.06 kilograms per cubic meter. Viscosity is dynamic viscosity is 20.1 multiplied by 10 power minus 6. Newton second per square meter. Thermal conductivity, 0.029. And Prandtl number is 0.696. Any other thing do we need? Specific heat. I will just note it down. 1005 joule per kg Kelvin. So these are the property values I need. Then I will calculate the value of Reynolds number, because our correlation is, see, the Nusselt number based on the diameter is equal to some constant multiplied by the Reynolds number based on the diameter power m, and Prandtl number power 0.333. So I need Reynolds number. Prandtl number is already known to us, 0.696. Okay, so Reynolds number is rho v d divided by mu. So rho is 1.06, multiplied by the velocity is 10, multiplied by the diameter is 37.5 millimeters. So 37.5 multiplied by 10 power minus 3 meters, divided by dynamic viscosity is 20.1 multiplied by 10 power minus 6. Tell me how much this is. So this is 19,776.1 is the Reynolds number. Okay. So in the table, we'll have to look for the values of the value C and M. So in the table, you will have Reynolds number based on the diameter and the constant value M and constant value C and constant value M. So our value is 19,776. So we have one range here for Reynolds number between 4,000, 40,000. The value of C is 0.193 and the value of M is 0.618. So using this, for us now, our range is, our Reynolds number is 19,776. Therefore, our Reynolds number falls in this range. Therefore, for us, this will be the value of C and this will be the value of M. So now we will use the Nusselt equation. C is 0.193 multiplied by the Reynolds number is 19,776.1 power 0.5 power M. M is 0.618. Multiplied by the Prandtl number is 0.696. Raised to the power 0.333. So this will give you the Nusselt number. And we are also asked another question. What is the drag force exerted on the pipe per unit length? Okay, this also we need to find out. You see here we have an equation for drag force. Drag force is portion of drag multiplied by A multiplied by rho v square by 2. So for us, the drag force, will have to read it from here. Our Reynolds number is 19,776. Okay, so that's close to 20,000. So this is somewhere in between. So this is what will be our value here? Somewhere here. So for the cylinder, we'll have to read it somewhere here. So it's close to slightly greater than 1.06. Our drag coefficient is 1.06. Now, what the formula to calculate the drag force is also available somewhere. Trying to find that. It is there. You don't have to remember that equation. Otherwise, you'll have to remember that equation. So you try to find out the drag force is coefficient of drag multiplied by frontal area multiplied by rho u square by 2, right? Rho v square by 2, yeah. So 1.06 multiplied by the frontal area. So what is this frontal area? So this area, whatever this region is. Okay. So how much will that be? The frontal area. This is the diameter multiplied by unit length. If the length is unity, we are told for a unit length. So length is 1 and diameter is 37.5. So frontal area is, I'll write the formula here, diameter multiplied by length. So diameter is 37.5 multiplied by 10 power minus 3 multiplied by length is 1. Multiplied by the density is 1.06 multiplied by a velocity is 10 by 2. So this will give you the drag force. So you should be getting 2.18 Newton meter. Newtons per meter of the cylinder length. 2.18 Newton per 1 meter length of the cylinder. Okay, so that is about the drag force. The Nusselt number, you can evaluate this value, find it out, and then use it in Nusselt. Nusselt is equal to HD by K. So find out the value of H and use that H value in Q is equal to HA delta T. Okay, so you can calculate that, complete that calculation. Now this A is different from this A. This is AF, which is the frontal area. This A is the total area. That means complete every side of this one. This is this circumference is pi d multiplied by L. So this A is pi d L, where L is unit length. So with that you complete this particular problem. Okay. So I'd like to stop here for today's class. And I guess this will be the end of our online classes. So we'll meet again in person on Monday. 10:45 is the class time. So I hope all of you will again see for the rest of this particular course. Make sure you bring your calculator, a notebook, and heat and mass transfer data book to the class, because we will be quite frequently, quite regularly using the data book and also the calculator. I want you to come prepared for the class. Your classroom is in AB 2703. Okay. I'll now take your attendance. Mrutunidhi.
Present, sir.
Abhilash.
Present, sir.
Can Sherian.
Present, sir.
Madhusudan.
Yes, sir.
Pranav Dilip.
Present, sir.
Siddharth.
Yes, sir.
Srivatsan. Maitreyan.
Present, sir.
Palanivel.
Present, sir.
Prishant.
Yes, sir.
Tamilalagan.
Present, sir.
Niranjan.
Present, sir.
Vaibhav Karan.
Present, sir.
Abhijit Menon.
Present, sir.
Pratik Krishna.
Present, sir.
Praveen.
Present, sir.
Adil Sinju.
Adil present, sir.
Chaturvedi.
Present, sir.
Chintan.
Present, sir.
Hamza Hassan.
Present, sir.
Ayush Tripathi,
Present, sir.
Harshavardhan, Hemant Kumar, Vishwa,
Present, sir.
Chandramouli Singh,
Present, sir.
Present.
Shubhania,
Present, sir.
Sai Rohit, Sri Raman,
Present, sir.
Vishal, Deepesh,
Present, sir.
Anirudh Venkat, Sri Kumaran,
Present, sir.
Sundar Krishna,
And Anirudh Venkat present, sir.
Present, sir. Sundar present, sir.
okay, Pranav,
Yes, sir.
Jayanti,
Present, sir.
Sriniket, Badri Narayanan, Sriniket,
Present, sir. Yes, sir.
Badri Narayanan, Avito, Ajit,
Present, sir.
Harish Raghav,
Present, sir.
Rahul,
Present, sir.
Firoz,
Present, sir.
Nihar,
Present, sir.
Vishnu Karthik,
Present, sir.
Gauri Shankar,
Present, sir.
Motishwar, Vijay Prakash, Suja,
Present, sir.
Prem Kumar,
Yes, sir.
Sharan Sarvesh,
Present, sir.
Sharan Ajay, Benold Simon, Vamsi Krishna,
Present, sir.
Venkatesh,
Present, sir.
Jnana Akshaya,
Present, sir.
Kiran Dev,
Yes, sir.
Varun,
Present, sir.
Kunal Rao, Vignesh Krishna,
Yes, sir.
Vedant Mathur,
Present, sir.
Vishwanand,
Present, sir.
Shivani,
Present, sir.
Riya Vasan,
Present, sir.
Kalai Priyan,
Present, sir.
Shankar Narayanan,
Present, sir.
Anish,
Present, sir.
Santosh Raj,
Present, sir.
Keshav Kumar,
Present, sir.
Akash Kumar, Kartik Prasanna,
Present, sir.
Sai Kaustubh,
Present, sir.
Varun Ahalyan, Sarvesh Krishnan,
Present, sir. Sarvesh Krishnan, present.
LC Femina,
Yes, sir.
Jeffet GNL,
Present, sir.
Amal Manoj,
Present, sir.
absentees quickly. Srivatsan,
Sir, Srivatsan.
Sir, present, sir. Present, sir.
okay. Harshavardhan,
Present, sir.
Hemant Kumar, Sai Rohit, Vishal,
Vishal present, sir.
Vishal,
Yes, sir. Vishal, sir. Present, sir.
Badri Narayanan, Avito,
Present, sir.
okay. Motishwar, Vijay Prakash, Sharan Ajay,
So, Vijay Prakash present, sir. My mic was not working, sorry, sir.
Sharan Ajay, Benold Simon,
Present, sir.
Kunal Rao,
Kunal present, sir.
Sir, Saranajay posted in chat box, sir, that he is present.
okay, I will see that. Akash Kumar,
Present, sir.
Varun Ahalyan,
Present, sir.
all right. So I'll see the messages in the chat box, so I can leave the class now. We'll meet on Monday.
Thank you,
Thank you,
sir.
sir.
Sir, this is Siddharth, sir.
Yes, that.
Sir, I have one doubt in